Hello, I'm Mike Douglas, and this is the New Technologies in Mathematics seminar of the CMSA at Harvard University. And today we're delighted to have João Araújo and Michael Kinyon, who will speak on from engine to auto, applying first-order theorem proving to prove many mathematical conjectures. So as I always do, I offer to watch the chat, and if you want to type a question into the chat, I'll either answer it if I can or relay it to the speakers. And feel free to ask questions during the talk, and we'll have a few minutes for questions and discussions at the end. So with that, João, please.
Okay, thank you very much, Michael, and thank you very much for the invitation. So mathematicians carry a number of operations. One of them for sure is proof. Mathematicians prove things. Another one is to create new objects. Mathematicians play the game of creating new objects and proving associate theorems for them. For example, we start with the axiomatic definition of groups, and then we move, we prove some theorems, then we introduce permutations and prove some theorems like a Cayley theorem. We introduce subgroups and prove some theorems like Lagrange theorems and so on. This is the game mathematicians play. Then we also conjecture by analogy. We have a theorem, and by analogy, we conjecture, we infer that probably another theorem is true. For example, suppose we have a singular matrix, a matrix non-invertible, and we take all the matrices similar to that one. These matrices are going to generate all matrices whose rank is at most the rank of the original matrix. Now we can conjecture. Imagine we have a finite set, and we take a non-invertible function from that set into itself. Again, take all the conjugates of that function and take all the products. What are we going to generate? Well, the result is essentially the same. Yes? Is there any problem? So this is a conjecture by analogy. We have a theorem, and we infer that possibly another theorem was true. And another operation of mathematicians is to generalize. When we see two theorems like this, the first thing that comes to mind is probably there exists a mathematical object that contains, as particular cases, vector spaces and sets, and in such an object, a theorem of this form might be possible. And in fact, we consider now a universal algebra, and we consider a set X contained in the universe of the algebra, and we say that set is C independent if no element in set can be generated by the remaining elements. And we say the set X is M independent if every map from the set into the algebra can be extended to a homomorphism. So these are two sensible notions of independence. And now we move on and we consider the class of algebras in which the two notions of independence coincide. And even more, the universe of the algebra, together with the closure operator, subalgebra generated by, is a matroid. You might say, this algebra is very artificial, but it is not. In fact, it is extremely natural because mathematicians keep stumbling upon it. So it was first introduced in Poland, and they proved very deep theorems about them. Totally unaware of that, there was a classification problem in model theory that was solved by Steve Givant in the US, and the solution was exactly this class of algebras. Totally unaware of all of that, Peter Cameron in the late 70s was working on permutation groups, and he came again across with this class of algebras, and totally unaware of that, Vicky Gold in New York in the 80s was trying to solve this problem I am trying to solve, and she introduced this class of algebras again. And in this class of algebras that, of course, contain, as particular case, vector spaces and sets, we have the theorem we were searching for. So mathematicians generalize when that is appropriate. Okay, so when Bill McCune in 96 solved the Robbins conjecture, a problem that has defeated Tarski, Giancarlo Rota, and many other equational logicians, it was clear that now or in the near future, one of the operations of mathematicians, proving things, was being taken care of by machines. The machine managed to find a proof that defeated some super mathematicians of the 20th century. And at that moment, we had an engine. The McCune's tool was an engine that now we had to wrap up in order to attain different operations, different goals, different functionalities, namely being able of creating new objects and proving theorems about them, being able of conjecturing by analogy, being able of generalize results. And the wrapper of this McCune engine is this machine called ProverX. There are reasons for this name. I will skip that for now. ProverX, in its very basic mode, let's say, in its brain dead mode, does what you expect. You can give some assumptions, some goals, some conjecture, and it finds a proof. So, and everything is written in a very natural language. For example, it took me 5 minutes to teach Friedrich Werung to use this language. 5 minutes, and he just published an entire book that he wrote just playing with this machine. And then, of course, this machine and much more. Then it also finds counterexamples when I try to prove that all groups are commutative. Okay, it just outputs the symmetric group on 3 elements. That is the smallest non-commutative group. And but as I said, this is the brain dead mode of working of this machine, because this machine can be controlled with Python, and the only limit is what you can do and the algorithms you can devise. The only limit on those operations, conjecture by analogy, generalize, do many things that mathematicians do. The only limit is your ability to devise algorithms to do that. For example, one thing that always appears in mathematics is that we want nicer presentations of a theory. Typically, the paper says, introduce a definition, and the next theorem says, the following are equivalent. And the first sentence is the definition we just introduced. Okay, this machine can do that for you in a lovely way. Let's say, imagine we have this problem, a class of algebras, a variety of algebras defined by these identities. We have a idempotence commute, we have von Neumann regularity, we have associativity, and we have a problem. Can this class be defined by 3 identities? This is a problem that comes from the 50s. And so we go to the machine. Just now I start, you can go to the website, enter as a guest. You can fully use the machine as a guest. You just drop an algorithm devised by Michael Kinyon, which is a brilliant algorithm, as I expect you are going to see shortly. And let me just pause here a little bit. What the input says is that we have idempotence commute is the first line. We have a von Neumann regularity. And then we are telling the machine to replace associativity and the other axiom by just one axiom. This is what we are telling the machine. So this is running in real time. I didn't cut the movie. This is the program running here. This is the time it takes to run. So the first thing he will do is to conjecture identities. He just finished conjecture identities that can replace those 2. And now he's trying to prove that at least one of them, in fact, replaces them. He's trying to prove a theorem. When he proves the theorem, in the column on the left, it will be a file called theorems. It will appear, so it appears, so he has a theorem. Here is the theorem. I will pause it a little bit. Here is the theorem. It says that the commutativity of idempotents and von Neumann regularity, together with this identity, that is a contraction of associativity and this one, they define inverse semigroups. So inverse semigroups can be defined by 3 identities, and this was found in less than 1 minute by this machine. Another example, suppose you have this quasi-variety. Quasi-variety, it is defined by this quasi-identity. And you happen to know, in fact, it is easy to know, that this class of algebras is closed for subalgebras, quotients, and direct products. So this class of algebras is a variety, so it can be defined by identities. And so the question is, can we find a set of identities which is equivalent to this one? And so we go to the machine. Let me just pause. Look, what I am telling here is that I have the 2 identities, and I ask the program to replace the quasi-identity by what? By something that avoids disjunction. This is the symbol for disjunction. So he is going to generate many candidates, but he will take only the identities. And then again, he's working without cuts. I am going to jump just a little bit. This is very fast anyways. And then he generates a number of candidates, and he already has the theorems. So here you have the quasi-variety is defined by identities, and here is the theorem. That is equivalent. These 3 identities are equivalent to these 2 plus this quasi-identity. Okay? So another example, imagine you work in an area of mathematics, and this model, for some reason, is very important for you. Is a critical model for you. Well, that book by Friedrich Verung that I referred to previously was written because he was conjecturing results, using the machine to find counterexamples, then doing reverse engineering of the examples and proving, guessing new conjectures and theorems, and eventually he had a book. In this case, this is not a group. It has no identity. And you would like to know what is known about this model. So again, you can come to one of these tools. It's freely available on the internet. You go to Model Explorer. You just paste in your model, search, and instantaneously, again, this is no movie cut. It tells you the papers where the model appears. As you see, the model appears in a different form, so he has to find isomorphic models. It tells exactly in the paper where it appears. In this case, it's non-commutative Riemannian geometry, but there were more papers where it is appearing. In this case, it is in knot theory, a paper in knot theory. There are more. This one is in quandles, a paper on quandles. And we can keep, and the last one is a paper on Nicolaus algebras. Again, the same model appears, and that's it.
João, is this basically a textual search, or is it some other kind of search? How is it finding that model?
It finds the model. There are several ways of finding the model. Well, maybe more than 90% of them, he searches tables in LaTeX. We downloaded the full database of the archive, and we produced a way of extracting tables from all the papers, and then get that. This was but then many have been introduced by hand and so on, and keep introducing. So there are many ways. Then to conjecture by analogy, we need the machine knows lots of mathematics. He can only conjecture things by analogy if he knows a lot. So it is obvious, it is connatural to develop this type of tools, to develop libraries. And many libraries have been developed. The library for first order logic, the main library, the largest one is TPTP, but that is not appropriate for our goals, because they basically use it to test performance of their tools, the new tools. Here we don't want that. We are not, our cup of tea is not that. We want real mathematics, new theorems, deep theorems, and so on. So what we need that our library has no noise, as TPTP has many noise. Here we need noiseless library. So we have many class of algebras, but algebras that appear in papers, in the real world. We have theorems in the real world that appear in papers with deep proofs and so on. And it is this that the library, I'm going to just quickly show the library. It is fully available. And you can see, for example, algebras of type 222. So with the 3 binary operations, there are many, like 3 semigroups and it's a Reef loop, etc., BCK, lattices, etc. So all this is the meat that then the machine will use to prove, devise new conjectures, the algebras of type 2-2, like rings, medals, demonoid, near semi-rings, pochrines, etc. There are hundreds of them, but all of these algebras are algebras of the real world, algebras that have been received the attention of someone. So then what happens? We just run results on the library. A trivial example. Suppose we have a magma that is a set with a binary operation, and consider the following relation. 2 elements are related if they are equal for reflexivity, or there exists 2 elements that satisfy this. This is just conjugation in groups, nothing. When S is a group, G is the inverse of H, and this just means that A and B are conjugate. This is a way of formulate conjugation when we don't have the inverse element available. So this can be used in semigroups of matrices and topological semigroups everywhere, where there is no inverse, no group of units. We can use this notion of conjugation. It is not easy to prove, but it is true that this relation is an equivalence relation on semigroups. Okay, but we run on our library and we just get this theorem. This is an equivalence relation on semigroups and also on directoids, on double word quasi-groups, in quasi-implication algebras, and so on. And now clearly, the first thing that comes to mind is there must be an object, an over object that contains all these classes, this particular case, and in which this notion of conjugation is still an equivalence relation, and in which we can prove many theorems about conjugate elements. For example, it is not easy to prove, but in a semigroup, if A and B are conjugate in this sense, their powers are also conjugate. This is trivial in groups, not trivial here. And there are many results like this. I don't know how much time I have still.
You have 10 more minutes, I guess, almost.
Then, so yet another library. This was produced with Peter Cameron, that I presume is here attending. So this basically finds a base of identities for a variety, for the variety generated by a given semigroup. So I am just typing here a semigroup, which is the Switzerland flag. And then here you can see the base. Let me pause a little bit. So this this semigroup generates a variety, and that variety is defined by these identities: chi square y equals xy, and it is commutative. So any identity that holds in this semigroup is a consequence of these two identities. Okay, this can be done, and it provides lots of information, like where this appears in the literature and so on. It also works for groups. For example, we have this group, which is the C4 times the symmetric group on 3 elements, and the base of identities for the variety generated for this group is provided here, and it says it was in a paper by Higman that this base was found, and so on. And it can also, it has a very nice way of finding the Cayley table of a semigroup given by any presentation, semigroup or group or whatever you want. So this is a problem on operator theory, that, and just the saying that that this semigroup has 17 elements was a paper in the Transactions of the American Mathematical Society. So this that took less than 1 second to this machine to find was then, when done by hand in the beginning of this century, was a paper in Transactions. As you can see, I am changing here the presentation. I'm just writing some crazy identities. So he immediately generates semigroup, finds the variety it generates immediately, and so on, the base of identities. And we have here conjectures for those interested, the hundreds and hundreds of conjectures. So this means that all these algebras here generated the same variety. This is the first conjecture. We don't know if this is true, but the computer conjectures this. And in addition, the computer said, probably this is a base of identities for that variety, or this is a base of identity for that variety. The algorithm we use to generate these identities was checked against all the cases up to order 5. And in all cases, it found a base of identities equivalent to a known base of identities. So this problem is solved for all semigroups of order up to 5. And the machine managed to find a base of identities for all of them, which is equivalent to the one that was found in the literature. Okay? And then we go to the last topic. Imagine we have this situation. We have a class of algebras that is A, that is contained in a class of algebras B, and there is a set of models F, a family of models F. It can happen that a model belongs to A if and only if it belongs to B and avoids the models of F. This can happen. And we denote that with this notation. The class of algebras A is the class of algebras B except the models of B that contain any element of F. Examples of this theorem: a lattice is distributive if and only if it does not contain the diamond or the pentagon. Another example: a graph is bipartite if and only if it does not contain a cycle of odd length. And so on. There are tens or thousands of theorems like that all over mathematics. And these theorems are very interesting because once you think that A is equal to B, this is your conjecture, then you come up with a counterexample. And rather than being depressed, you could think that maybe that counterexample or those counterexamples tell the whole story. No, A is almost equal to B. A is equal to B except for the models that contain a finite or a well-described family of models. And we also produced a tool. This is, again, you enter as guest. You you can write the larger class. The larger class is the class which has the axioms on top and below. So here, and you just ask for a theorem. And again, it is live. I am not cutting the movie. It takes this time, and it finished, and it proves the theorem. An algebra satisfies these axioms if and only if it satisfies the two first and avoids these two models. The program found the conjecture, found the models, found the conjecture, and then proved the conjecture and give the theorem. And this works for algebras, any algebra, relational algebra, therefore graphs, it works for everything you want. It's just there. Just a proof of concept in 2021. These authors proved a description of all varieties of lazy groupoids. The semi-lattice is like this. As you can see, there are lots of containments. U is contained in L1, U is contained in L2. So this for just a proof of concept. What can our program do with all these varieties? Can we prove a forbidden substructure theorem for each one of these containments? There are 16 of them. And the program found theorems like this. An algebra belongs to something I can't read, but I guess you are reading this statement. It found the models, it found the conjecture, it proved everything. There is no human intervention here apart from giving the two class of algebras. Even more complex, this theorem has a very complex proof and long, but the computer found it very quickly. Again, a brilliant algorithm that Michael Kinyon devised is behind all that, all these achievements. So there are 16 theorems to prove, and the machine proved all of them. So L6, U can be characterized inside L6 by this theorem, here and so on. Everything. All containments are were automatically characterized by the computer, and that's it. I just would like to tell you, this is a fascinating topic. The key is to devise the nice, the good, the beautiful algorithm that makes everything work and allows the machine to perform those extra operations more than just proof, conjecture by analogy, generalize, and so on. Thank you very much. Now it's Michael.
Okay, let me share my slides and whoops, there we go. Okay, so let me also add my thanks to Michael for the very kind invitation to give the second part of this talk. I should warn you a little bit in advance that although João and I were following a general outline for how the two parts of this talk were going to go, we did not rehearse this. So the styles are going to be somewhat different. I have a somewhat more traditional Beamer talk here. In addition to that, there might be some overlap. I will be talking about some of the, not all, but some of the algorithms that João alluded to in the first part. I'll be talking about them in general terms just to give the idea of them rather than the details. Okay, so first of all, I should probably make a comment about this, because if you talk about machine theorem proving or computer-based prover theory, excuse me, theorem proving to mathematicians, they tend not to think of automated theorem proving. They probably think first of interactive theorem proving. And the reason for this is that in recent years, especially the last couple of years, interactive theorem proving has been enjoying another uptick in popularity. It had one back in the mid 2000s and is having another one right now. And so the most popular theorem, interactive theorem prover right now is probably lean. And what interactive theorem proving is mostly about formalization. So taking existing mathematics, formalizing it, and using it as a way to verify the correctness of extremely difficult theorems or structures and so on. The interactive theorem provers may be linked to automated theorem provers to handle some tasks, but that's not the primary use of them. Now, as João was indicating, the tools that he and students and so on have developed have a foundation of automated theorem provers directly. And we're more interested in as he said, that we're more interested in the direct use of these things to discover new mathematics and settle conjectures rather than to formalize existing mathematics. Now, João pointed out that most of the tools that he was looking at and he was showing you were based on prover X. Prover X sits on top of a more familiar, well, not more familiar, I shouldn't say that, of a known automated theorem prover called prover 9, which was actually developed by McCune, the same person who solved the Robbins problem using an earlier theorem prover. There are several, and I would like to make a comment about this because I don't think there are any people in the audience for whom this is an issue, but we're often asked why we base things on tools sitting on top of prover 9 instead of other theorem provers, many of which are actually preferred more by computer scientists. And there are several good theorem provers. I have nothing disparaging whatsoever to say about them. They're just, however, prover 9 has certain advantages, which you actually saw in João's half of the talk, which is that the input language is extremely easy to read and use. For mathematicians especially. You can basically use it right out of the box and read it and understand exactly what you're doing. While with most other ATP systems, there's a process of translation into the very peculiar input language of those systems. In addition to that, prover 9 has some powerful features which were built into it by McCune, which most of the others don't have, or they have only to a limited degree. And some of these are, in fact, the foundation of the algorithms to which João was alluding. Now, the other thing is that, as you already have seen, while all-purpose automated theorem proving systems can do a lot of different things, first-order logic and so on, where they really shine is equational reasoning. And this has been true since the early days, especially since McCune first solved the Robbins problem using his early theorem prover EQP. And one of the things that this means is that when you formulate a problem for an automated theorem proving system, you sometimes have to lower the level of the problem in order to get it down to something that an ATP system can actually manage. It's one thing to just sort of think like a mathematician and formulate everything at a very high level, but if you do that, you run into danger that your theorem prover is not going to be able to really make much progress with it. Let me give you just a very simple example of what I'm talking about. Let's suppose, for instance, that we think about what it means for a group to have nilpotency class 3. Now, there are different ways of defining this, but as mathematicians, we usually think of it as saying that there is an upper central series with 4 terms in it, the last one being the relevant one equaling the group, and where all these various quotients in this series correspond to the centers of the predecessors and so on. So I don't need to read this to you, but this is all very, I mean, this is high level type of definition. It is, however, how we usually think of this. But you can express nilpotency class 3 by a single identity, or more precisely, nilpotency class at most 3, which is just simply to write down an identity in terms of commutators. And this is an example of how you would take a fairly high level thing. This is an elementary example, but how you would take a high level idea and formulate it for something an ATP system can actually work with. So for instance, here's what the input would look like if you wanted to prove a theorem. I don't have anything in mind, but if you want to prove a theorem about groups of nilpotency class 3, okay, you just write down group axioms, define a commutator, and write down the condition that I just said, and then try to prove whatever it is you want to try to prove. Okay, now I'd like to tell you the story of how I got into all this business, which is a story that goes back to about 1999. To do that, I need to backtrack a little bit and do a little bit of mathematics here. So I need to tell you about quasi-groups and loops. One thing that is very characteristic of the usage of automated theorem proving is that it's extremely effective in areas in which there are open problems which can be translated into first order form. So for instance, a lot of problems in group theory that still exist, this can't really be done in a reasonable way unless you're talking about problems in commutator calculus. Quasi-group and loop theory, which I work in, is one area where there are still a lot of open problems that can be translated into first order form. Okay, so I need to tell you a little bit so I can tell you the story. Okay, a quasi-group is just a set with a binary operation such that certain equations can be solved, and examples include groups, and a loop is just a quasi-group with an identity element. I won't go into the apocryphal story of how loops got their name. The main thing to just take away from this is that if you're thinking about a finite case, the multiplication table of a loop is just a reduced Latin square, like this, where the one is playing the role of the identity element. And you can see immediately that this is not a multiplication table of a group because it has an element of order 2 in it, even though it has order 5. Okay, so, but more importantly for an ATP system is that a quasi-group or a loop can be characterized equationally. There are in fact, 3 binary operations really underlying this, the multiplication and 2 divisions, and you can completely describe what's going on just by universally quantified equations. And that means that quasi-groups and loops form varieties in the universal algebra sense of the word variety. And this is what's really better suited to using in an ATP system. So I'll tell you what a Moufang loop is. Here are some identities, and if your eyes glaze over as soon as you see them, that's good. That means you are paying attention, because mine certainly glazed over the very first time I saw these two, and they do not matter for the rest of this talk. I was just simply giving you a precise definition. What's important is that there are many natural examples in mathematics. Besides groups, the non-zero octonions, the 7-sphere with octonion multiplication. There is a very large Moufang loop called the Parker loop, which is used in one of the constructions of the monster group, and there are many other places where they occur. Okay, a little bit more, and then I can tell you the story. A loop is diassociative if every subloop which can be generated by no more than 2 elements is associative. Okay, so this means if you write down an expression in just 2 variables, it associates freely and you don't have to worry about parentheses. Moufang loops actually are diassociative. This is a consequence of a much deeper theorem by Ruth Moufang herself. Okay, and finally, in a loop, we also have various permutations that act on it, left and right translations, and these generate various groups. There's the multiplication group, which we don't need to worry too much about, but more important is the intermapping group, which is the stabilizer of the identity element, and of course the automorphism group, which you have for any type of structure. All right, so with all that said, we now get to the open problem, which is where the story all begins. A loop was called an A loop, or just automorphic loop, if every intermapping is an automorphism. So this is a high-level condition. And these were introduced back in 1956 by Bruck and Page. And this is the very last time that a paper on quasi-group and loop theory appeared in the annals of mathematics, or at least so far. They posed a problem, well, sort of. which is every diassociative A loop. So is every one of these A loops which has the earlier property a Moufang loop. Now I should say, in fairness, they didn't actually phrase this as an open problem because Bruck was not in the habit of stating open problems in his papers unless he already had a very good idea how to solve them. So this is more of an implicit question in the last couple of paragraphs of the paper. Now, how do you turn this higher level problem, in keeping with the theme, into a not so high level problem? Well, the point is that the inner mapping group has a set of generators, which can be formed from the permutations. And the consequence of this, you don't have to really pay attention to what the generators are, but the consequence here is that the high level condition that says that every inner mapping is an automorphism can be expressed as 3 universally quantified equations. So here is the whole story. I apologize to those of you who've seen this before. The person on the left is what I used to look like back in 1999. The person on the right was my collaborator at the time, J.D. Phillips. This is what he looked like back in 1999. As now my hair is magnificently silver and he doesn't have as much as he used to. And here's what happened. The problem that Bruck's Page's problem was posed to me by JD and by email, and we discussed it for quite some time. We went back and forth on it through several exchanges of just to see if we could get anywhere with it, and we got absolutely nowhere. And we didn't really know what to do. Now, at the same time, there was a third person who was being CC'd all these messages because she had been part of the conversation earlier before this got started. And this was Hala Flugfelder. And she suggested that we go ask Kinyon, a name that was probably familiar to many of you. And except in 1999, I didn't know who that was. JD, however, had a set theory course in grad school, and he knew who it was. And we found out that he had been proving theorems about loops using computers. And so we decided, sure, why not? Let's go ahead and ask him. No harm trying. And here's what Ken Kunin, who sadly died a couple of years ago, looked like back in 1999. We posed the problem to him, and he thought it was quite interesting. And then that was all we heard from him for a while. So we just waited, and also thought about the politeness because we were both young assistant professors at the time. And then about a week later, we got a message and a very ugly proof, which he attached to the message. I'm not going to show it to you because I no longer actually have a copy, unfortunately. This was a long time ago. And that's where the story all begins. Now, I'm going to talk toward the end about proof simplification. By the standards, by the proof that was originally sent was about 300 steps long. By today's standards, that's not a very long proof. But at the time, it seemed amazingly daunting. Now, I didn't even know how to run Otter, which was Prover9's predecessor, or anything like this. We tackled the problem of humanizing the proof in front of us, and we were able to produce a much more readable version by reintroducing high-level concepts. The same thing generally happens in a lot of cases where we try to publish results in this. Sometimes it's very helpful to actually take the proof that's given to you by an automated theorem proving system and see if you can actually maybe recognize things in it that can be translated back into high level. So a lot of what I do, in fact, in quasi-groups and loops or semigroups or non-commutative lattices and some of the other areas that João was alluding to in his part of the talk, is try to find equational formulations of problems, or quasi-equational in some cases, see if what Prover9 has anything to say about them, and if possible, if feasible, humanize the proofs. And sometimes it's not, and I'll show you an example later at the end of the talk where this doesn't really make any sense to do. So at the moment, the biggest success in this was a very hard problem that was just solved last year in loop theory, where some of the lemmas have proofs that are several thousand steps long. And there's just no way that these are going to be humanized. I mean, you might say, well, give it to a grad student to do. Well, not even I would be that cruel. So what I'd like to do is talk about some of the things that João was talking about in his demonstrations and the underlying ideas behind them. Not all of the things that he mentioned, but some of the general algorithms behind them. Prover 9 has a very useful feature, which is called semantic guidance. And the idea is that you include, along with your input, models, as João was talking about, in which key axioms are false. And which ones are the key axioms is something the user should decide. Then what happens in semantic guidance is as the prover generates new clauses, it evaluates them against the models. And if any of those clauses are false in those models, it just marks them that way. It doesn't mean that they're false clauses in general. It just means they're false in those particular models that it was comparing them to. Okay. As Prover 9 chooses clauses to make new inferences, it then favors the ones marked as false and chooses them early. João was actually already talked about this, so I'm going to allude to exactly how it works. So the original intention of semantic guidance as designed by Bill McCune was just straight up theorem proving. The idea was, if you focus on descendants of more important axioms in your algebraic structure, then maybe you can steer a search for a proof in the better direction more quickly. And it can help with that, although to be quite honest, I rarely use it for that purpose. Other techniques tend to be better. But João and I use semantic guidance in a much different way than intended, and he showed you some examples of that in his demonstrations. So here's the idea. Suppose we have an algebraic theory where one of the axioms is a universally qualified implication. Okay, universally quantified implication of this form, or there can be more equations on the left part of this. And the question is, can this be replaced with an equational identity? Now, why would anybody care? Well, as João said, the high-level reason that you might care is because if a theory can be expressed entirely equationally, then you automatically get for free that the objects in the theory are closed under taking homomorphic images. That's the really high-level important thing here. So the idea of the algorithm is to use semantic guidance. This is just kind of a general sketch of how it works. Find a model in which your implication there is false. Run Prover 9 for a while, not with the purpose of proving a theorem, but just to generate some output, just to generate clauses, and see if and make sure that your false implication is one of the axioms, meaning false in the models that you have put into the input. Then look at your output and see if any of the consequences of the false axiom have also been marked as false. Those must be descendants of that axiom, because that's the only reason they could possibly be marked as false. And if they happen to be identities, then they are candidates to replace your implication as a new axiom. Then just check if the identity that's generated implies your original implication. If it does, great, you've got a new axiom. If it doesn't, then you have some more models that you can throw in and rerun and try again. When this works, it works great. Sometimes it doesn't work, which is fine. And it sometimes works extremely well. My personal first success with this was when I was working in non-commutative lattice theory. A non-commutative lattice is exactly what it sounds like. It's like a lattice, except you just throw away the commutative laws. And there was an open problem in that area to show that cancellation laws are equivalent to something like distributive laws. In other words, that you could actually replace these implications like this one, for example, and others that look similarly with identities. And Prover 9 was just wiped this out in like about an afternoon. I did the whole thing in an afternoon, essentially, and then sent it to the person who had posed the problem. Now, what's interesting, and just to give you an idea, that there are limitations. Sometimes prover 9 will struggle with things, and so will all automated theorem provers in this case. In regular commutative lattice theory, the same problem is actually harder for prover 9, and the reason is not because the algorithm is poorly designed. I prefer to think that it isn't, but rather because there is a curse of commutativity that often haunts automated theorem proving. If you have problems that are highly symmetric, then the search space can grow too large, and they can have trouble finding proofs or finding whatever it is that you're looking for. In a similar way, João showed you a case of reducing axioms, that is, reducing the number of axioms in a algebraic theory, and he showed you the example of inverse semigroups. So this is not a very mainstream thing to do in mathematics today, but in the first half of the 20th century, it was quite au courant. So here's the idea of the algorithm. Suppose we want to replace two axioms with a single one, okay? And so we have a theory, we have a bunch of axioms, we single out two of them for replacement. We find a model in which the first axiom is true and the second one is false, and also vice versa. And then we run the entire theory with both models in the input. If prover 9 generates a clause which is marked false, that must be a descendant of both of the axioms. And we check to see if the new clause implies both axioms, and if so, we're done. We get a new it works, otherwise we repeat. Again, sometimes it works, sometimes it doesn't. Here is the set of 3 axioms that João already showed you in his demonstration for inverse semigroups that this algorithm found. And later, the algorithm and some human ingenuity, we found 2 axioms that will suffice, although this one was assisted by greatly assisted by human work. Now, I should say, we're not pretending that the theory of inverse semigroups or anything else is revolutionized by finding reduced axiom systems for them, okay? However, these things are out there, and there are problems posed of this sort. If you're wondering why we do this, I'll just remind you of the motto of aperture science: we do what we must because we can. So what I'd finally like to talk about, I see I'm almost running out of time, but that's okay. I'll just, I can wrap up pretty quickly. I'm sorry, Michael, if I'm running over.
You can take a few more minutes.
Okay, I'll wrap up real quick. So for the rest of my time, I would have talked about the forbidden substructure theorem, but I think I'd prefer to talk about proof simplification. And because I think this is of some interest. When an automated theorem proving system finds a proof, it simply spits out the very first proof it finds after wandering through the search space and looking for something. And I can tell you that this is never, by any stretch of the imagination, an optimal proof. It's usually not simple, it isn't elegant, or anything else that you might want it to be. It's just the first proof. It is actually possible to use prover 9 to find simpler proofs. Again, this is a feature that other ATP systems don't really share. Now, to do this, I have to quickly tell you about the proof technique called proof sketches, which is implemented in prover 9 by hints. The idea is to do things the way mathematicians do them. If you want to prove a theorem in a particular general theorem, so you want to generalize, as João was talking about in his talk, the first thing you might do is prove the theorem in a more specialized setting. And then, if you're lucky, it can often be the case that the proofs of both the special cases and the general case will have features in common. And what would be great is if you could guide your automated theorem proving system in the direction of the proof of the special case as it attempts to prove the general case. So for example, let's say you want to prove a theorem about distributive lattice, and it turns out to be a very easy theorem to prove in Boolean algebras. So you might work your way up the lattice hierarchy. Modular ortho lattices and orthomodular lattices and other things with ortho and complemented and stuff like that in the names. It doesn't really matter what all these things are, until finally you get to distributive lattices, and maybe you can get a proof out in that case. And in each time, you're using the previous proof to guide the search for the new proof. The idea is that a proof is just a sequence of clauses, and if you have a if you have an extra assumption in your target theory, okay, and that you want to get rid of, in this case marked by CI, then you have to just simply bridge the gap. You either need to find a new proof of the later clauses in your, or you need to somehow jump over them. And in either case, you've hopefully created a simpler problem. Now you can get good proof sketches by hand, but this is almost never happens. Instead, what you do is you prove the theorem in a stronger theory, extract the proof, and that gives you very good sketches. That's really the case of interest here. What does this have to do with simplification? I'll get to that. This is implemented in Prover 9 through so-called hints lists. When a new clause is generated, the Prover 9 checks if the clause matches or subsumes a hint. So let's say you already have an existing proof. Let me skip this slide because I'm running out of time. Then what you do is you extract the hints from the proof and you run again without changing any input or any other settings. So this time we're not trying to generalize, we are trying to simplify. Now you might expect that Prover 9 will find the same proof, but that's not what happens. And the reason is because clauses are now being generated in a different order as new ones are being selected because of the presence of the hints. And so the butterfly effect sends your search off in a different direction, hopefully a good one. And we keep rerunning using using each subsequent proof as hints, and also squeeze various parameters such as maximum variables and so on. And what almost always happens, not always, but almost always, is that a simpler proof will result, as measured by, for example, its length, which is a naive way to do it, but that's a very easy one to work with. Okay, now why am I doing this? And now I can wrap up. So the most practical goal of simplification, besides is humanization. If you want to humanize an ATP proof, it would be better if it's a simpler proof because it's easier to work with. I mean, and that's still a lot of what I do. In order to make journal editors happy about a proof that I found, you want to replace first order equation bashing with higher level reasoning, and working with a simpler proof is a good way to do this. But there are also reasons why simplification should be done for its own sake. Here is a lemma from that theory I was alluding to earlier, and it has a proof that has almost 73,000 steps in it. Okay, only a crazy person would attempt to humanize this proof. And this is one actually where simplification doesn't help a lot. You can bring it down, but not much. This is not humanizable, and to be honest, there's no reason we ever should. But if we're going to archive such proofs, make them available for people to consult later, or for more sophisticated systems to look at later, it would be best to have them as simple as possible. And I'll stop there. Thank you very much.
Thanks. Thank João and Michael for a very informative talk. Questions from the audience? Well, let me. I mean, it's very interesting to see these things used. I mean, I haven't used first order provers myself. I mean, there's some analogy with what I do more as a physicist is computations, and of course there's symbolic algebra, and then once you have a device which is a tool, you do think of these clever ways to use it, that aren't just calculate from A, B, C, D, and so forth, and so some part of what you're doing is that, although you stress that you're doing automatic theorem proving, a lot of your work doesn't look automatic at all. It looks rather hands-on, the way you use it. Is that a fair statement?
João, you want to go first?
Michael, please.
Oh, okay. Yeah, Q&A sessions with two speakers are always challenging, right? I would say that's somewhat fair, at least in my case. I mean, certainly, in order to design these kind of strange algorithms for using the provers in ways that they really were never intended for, did require a lot of getting my hands dirty with some of the details. And there are certainly, for difficult problems, such as some of the ones I was alluding to, it is certainly the case that ATP systems cannot really be treated like a black box. You can't just punch the button, prove this, go off, get your coffee, come back and hope for the best. I mean, you do have to sometimes really get in there and mess with things if you have a particularly difficult problem. One of the nice things about some of the stuff that João has done is that it is making many of the aspects of these things more automatic, as we saw in his demonstration. João, I'll let you take over from here.
Yes, this is the two parts of the world, let's say. One is the computer scientists. They are trying to make more strong provers that prove more, solve more problems and faster. More problems and faster. But there is this part of the world where are the mathematicians, and this is an extremely interesting field for mathematicians. This is extremely interesting. As Michael said, this is not just a matter of encoding a problem and go sleep and come. This never happens. So no problem, no interesting problem works like that. And always a paper is a measure of added value. And now is the same thing. Papers are measures of added value. The difference is that with these machines, we can add value that was impossible 20 years ago or 30 years ago. So we can prove in seconds what the greatest mathematicians of the past could not prove in their entire life. And but to keep us on the limit of the challenge, we are always searching for new challenges, new algorithms, new ways of proving, try to do new things. This is an extremely interesting. It is completely the opposite of a very boring life. You just encode the problem and get the machine doing it. No, by no means. And then this requires usually Michael slightly alluded to that. You encode a problem in a way and you get absolutely nothing. The machine is running. Then you make a slight change and it immediately gets the result. And so this requires a deep mathematical knowledge to see that what we're trying to prove can be proved also in that way, can be reduced to that way. And this is also very interesting for students. Students learn how to pay much more attention, because a small mistake and they thought they were going to have a theorem and then get a counterexample. And so devising these theorems is a fascinating hobby or activity, and pushing all this to the limits is I think it's an area of mathematics in itself for mathematicians. I think it's an area in mathematics to itself, and in some sense it is a difficult time for these pioneers, because we have a beautiful algorithm, and what are we going to do with this algorithm? So journals in computer science usually are not interested in an algorithm that allows you to prove a certain type of theorems. And journals in mathematics usually are interested on the result of the algorithm. But the best part is the algorithm itself. And by now it's in no man's land. It's a bit, I think. So I don't know if I answered your question.
Oh, it's interesting. More questions from the audience, or please? Yes.
Hi, I'm Peter Gibson. I have question
Peter.
about very interesting talk, by the way, and I really enjoyed hearing about prover X, which I regret to not have used yet, but I'm looking forward to using all the different aspects in which it was involved. And the Marcy X noiseless library sounds very interesting. So I do want to say that I'm very happy that proof simplification is getting some attention. It should, because it's automatable in some sense. It's more easily automatable than finding proofs, but it's not considered a very important area. So I was wondering, I mean, to what extent do you think that the approach that you've used could be adapted to other engines? Because there are lots of them out there, and we want to make sure that that we don't just get stuck with one engine, right?
No, I mean, that's quite right, because as I mentioned in the talk, and as you know quite well, Prover 9 is legacy software at this point.
Yeah.
The only one I can think of where I think this could be adapted is the ATP system E, because it has a type of proof sketches implementation in its so-called watch list. It's not, to be honest, it's not the most sophisticated one. I don't think any of the others proof simplification can really be done in this way. Because in all the others, you just run things from scratch and hope you get a different proof without any parameters from your previous one. So.
May I say something, Michael? In fact, the Prover X got his name because he arrived at the same time that iPhone X arrived, but also because Prover X comes after Prover 9, and also because Prover X has many provers. Like if it was a variable prover, it has Prover 9, but many others. So it has a translator. It has a translator from that very comfortable language of Prover 9 to the other provers, to Vampire and E and so on. And it usually sends the jobs to all of them, and the first one finishing kills the others. And many times it is not Prover 9, the first one. Right. It can be Waldmeister, can be Vampire, can be E, and so on. And then what we do is that we get the proof from the prover. Doesn't matter, Vampire. We get that prover and use it as a hints for Prover 9. And then we also have a tool that does automatically that game that Michael described. So we use the proof found by another prover to guide the proof of Prover 9. And then finally, Michael, Prover 9 is not legacy because it has been rewritten, entirely rewritten, Prover 9 and Maze 4, and they are much faster than the original now, the new versions, and they will be maintained forever or for the next 10 years.
Wonderful. Well, thank you very much. I'll be in touch.
Forever or the next 10 years, whichever comes first.
Can you tell us an example of an open problem along these general lines that you think might be solvable this way, but you haven't solved it yet?
Well, there are zillions of problems.
Sure.
The fact is that I am a little bit tired now, but I can send you an email with many problems. many.
Okay.
What time is it?
It's
no for João.
That's right there. It's 8:11, I guess.
But there is still the LAM conjecture is still open, right? The M conjecture is still open, Mike.
Yeah, the strong one is still open, and it's a problem I've been working on with Bob Viroff in using these sorts of techniques for many years now. Progress is incremental.
There are many problems.
Of course.
Families of open problems. At 8 in the morning, I am able to tell some.
Okay. Any more questions? If not, well, let's thank again, João and Michael for.
Thank you.
Talk.
Thanks
So
very
we'll
much for the
be-
invitation.
Thank you very much, Michael.
Okay, so we'll be taking a break for the rest of November in this series, and we'll come back in December. So thanks, everybody, and thanks again for a great talk.
Okay, thank you very much. Bye.
Bye.